We have seen the orthogonality, the basics in the last lecture. The orthogonal vectors, the vectors are said to be orthogonal if they are perpendicular to each other, if they satisfy the Pythagoras equation. Now the length of the vector, let's repeat what all we have seen briefly. The length of the vector is nothing but, that is, in case of this, the length of the vector is hypotenuse here, and it is diagonal in three-dimensional coordinate system. In three-dimensional coordinate system, we can write it as x1 square plus x2 square plus x3 square, and in two-dimensional system like x and y, we can write it as the vectors are these are the vectors, and the length is given by the hypotenuse length, which is equal to 5, that is 1 square plus 2 square. And similarly in three-dimensional coordinate system, it is x1 square, x2 square and x3 square, the sum of the axes. And this we have applied with the n-dimensional. For n-dimensional space, we have written it as, so it can be written as the magnitude of this x is equal to x1 square plus x2 square plus x3 square and so on up till xn square if our dimension, or if we are looking for the space, are n. Even this x, by the Pythagoras theorem, this x magnitude of square, this x square can be written as, or it is equal to x transpose into x, or even x into x transpose is true, and it gives the same length. For example, if we take our x is equal to, if we are taking our x is equal to 1, 2 and 3, if we take x is equal to 1, 2, 3, then x square, magnitude of x square would be equal to the magnitude of 1 square plus 2 square plus 3 square, which is equal to 9 plus 4 plus 1, so that is 14. Similarly, we can check it here. So x transpose, now x is equal to 1, 2, 3, it has to be written in the column space as we know. So but as it is a transpose, let's write it as 1, 2, 3, and x is nothing but 1, 2, 3 in the column space, 1, 2, 3. Is equal to 1 into 1, that is 1, plus 2 into 2, that is 4, plus 3 into 3, 9, so which is equal to again 14. So even the magnitude of x square is equal to, the magnitude of x square is equal to x transpose of x. It is always true. Now let's look for the orthogonal condition. For orthogonal vectors, as we saw in the last video, the magnitude of x square plus y square is equal to x minus y the whole square. The meaning is a square plus b square is equal to c square. So it is true with any of the dimensional coordinate system, or it is true with the n-dimensional space also. So x square plus y square is equal to x minus y the whole square. What is this? Let's see. So x square, so this is x and y, x square plus y square, x square plus y square, the magnitude square is equal to is equal to x minus y, x minus y the square. The meaning of this is the Pythagoras theorem itself. Now the length of this is 1 and the length of this one is x, as we know how to find the length of the vector, the individual length of the vector. So it is nothing but x square, the same as it is, plus y, means it is y square is equal to. Now if I draw a diagonal, now it is a hypotenuse. If this is a right angle, then certainly it becomes hypotenuse. For this hypotenuse, the length has to be given. Let's say it is a c, means it is representing c. How do we calculate this c? Either it is x1 minus y1, x2 minus y2 and so on, or it is y1 minus x1. So generally, let's write it as in terms of point, that is x minus y. So it is x minus y, which is nothing but the c. And when we expand, this x is nothing but sum of all these x1, x2s and all, as we can see it here. And y is nothing but sum of all those x1 terms, x2 terms and all, x1 square and so on. And then it is the sum of y's, y1 square, y2 square and so on. And this is equal to x minus y the square. We know how this x minus y the square has to be calculated. So that is equal to x1 minus y1 square, x2 minus y2 square, xn minus yn it is. So now x1 minus y1 square is expanded as x1 square plus x2 square minus 2xy. Means on the right side we are having this minus 2xy term as an extra. So to be the orthogonal vectors, the sum has to be this x square plus y square should be equal to, will be generating x square terms, y square terms plus this extra minus 2x, 1 by 1, x2 by 2 like this. And these are to be 0 to make these sums as equal, otherwise they are not equal. And the condition to make them as equal is, now let's see here, if for orthogonal vectors x transpose y should be equal to 0. So what is x and y? X is nothing but our one vector and y is another vector. So x transpose means transpose of one vector multiplied with another vector should be equal to 0. Then only the vectors are said to be normal or orthogonal to each other. Otherwise, they are not orthogonal to each other. So x transpose y should be equal to 0. So the sum, that is, when this condition is satisfied, then certainly these all terms like 2x, y, those were there, they all go to 0, and that x square plus y square will be certainly equal to this, the magnitude, that is x minus y the square. So it would be just equal to this. So if these terms get cancelled, it is x square plus y square terms. So both RHS is equal to LHS. So those would be normal to each other. So this is called as inner product. The inner product x transpose y is equal to, so for n dimensional we'll be having xn components, as we can see, n number of components. So if this gets multiplied with, if the transpose of this gets multiplied to the y vector, if the transpose of this is multiplied to y, then it would be x1 y1 x2 y2 in this way, and if this inner product turns to be 0, then our vectors are said to be orthogonal to each other. Let's see what is the condition. Now for example, now our x is 4 2 and y is minus 1 2, and when these values of x and y are given to us, 4 2 and minus 1 2, x and y are these. Let's check whether this condition x transpose y is what. So how to check this one? So x is 4 2, y is minus 1 2, x transpose y. Now x is 4 2, its transpose is 4 2. Transpose it is, then y. It gets multiplied with y, that is minus 1 and 2. Let's multiply this. 4 into minus 1, minus 4. 2 into plus 2 into 2, 4. So we'll get 0. So as we get x transpose y, then the result is x transpose y is 0, means both these x and y are normal to each other or orthogonal to each other. Similarly, if this point could have been like, if x is 4 2 itself, and if we are finding another point of y such that x transpose y makes it as 0, then even it could be the combination like minus 2 and 4 also, means which all are the multiples of this y can be orthogonal to this 4 2 for this x. And see, if I take this one as minus 2 and 4 here, then also 4 into minus 2, it is minus 8, and this 2 into this would be 4, that is 8, minus 8 plus 8 would be 0. So all the multiples of this y by keeping x would make the orthogonal vectors of x, and even the converse is true. X transpose y, if it is equal to 0, then we can say both these vectors are normal to each other. If x transpose y is greater than 0, if the greater than 0, the angle between the two vectors, let's say this is one vector and another vector, if both of these x transpose y are given is calculated, and if it is greater than 0, then the angle between them is less than 90, and if x transpose y is less than 0, then the angle is greater than 90. The same is being highlighted over here. If the inner product x transpose y is 0, we can conclude that the two vectors in two-dimensional system, or it may be in n-dimensional system, are the orthogonal vectors. For example, this 2, 2 minus 1 is orthogonal to minus 2, 2, 2, because when these are multiplied, they are giving both have their length equal to 3, that is root of 9 is equal to 3. Then one of the useful factors that if non-zero vectors like v1, v2, v3 and vk are mutually orthogonal, if k number of vectors are there and if they all are mutually orthogonal, then every vector is perpendicular to every other, then those vectors are linearly independent. Since this is one of the conditions, the linearly independent vectors are usually mutually orthogonal to each other. So the proof for that one is, let's consider the linear independence equation, the linear combination equation C1 V1 plus C2 V2 and so on up till Ck Vk is equal to 0. To show that C1 must be equal to 0 to be like linearly independent, we'll take the inner product of them. So for that C1 V1 this all, when we go for linear product, when we go for inner product, so we have to multiply this V1 by V transpose, then V transpose, V1 transpose, let's say with the first one, V1 transpose of this vector is equal to C1 V1 transpose into V. We can write in this way, and we know that as this v1, v2, v3 and so on are the vectors, and they are non-zero. As they are non-zero, their product v1 transpose v cannot be equal to 0. So as it is not equal to 0, as the vectors are non-zero, v1 transpose v1 is not equal to 0. So this indicates that c1 should be equal to 0. And if the constants are equal to 0, then the vectors are linearly independent. And we can say that we have the knowledge of two-dimensional coordinate system, three-dimensional coordinate system and so on, as we are already known that. The coordinate vectors e1, e2 up to en, e indicates the identity vectors. So it may be any dimensional, the identity vector, the identity column vectors, let's say even, that is 1, 0, 0, whatever is the dimension. So these all are orthogonal. For example, in three-dimensional coordinate system, we have our x in this way, y horizontal and z are normal. So the vectors corresponding to these, or the unit matrix corresponding to this is this way. So first one is x. It indicates 1, 0, 0. Corresponding to y, it would be 0, 1, 0. And corresponding to z, it is 0, 0, 1. So this is our even in a three-dimensional coordinate system, E2 and E3. So it may be any dimensional coordinate system. If it is a two-dimensional coordinate system, just x and y would be there, 1, 0 and 0, 1. If it is four-dimensional, then first one is unity, the rest one. So the meaning is these all the identity matrix column vectors represent the orthonormal basis, because these all are the basis of that system. These all form the basis. So if whenever the magnitude of the vector is 1 and if the vectors are normal to each other, they are referred as orthonormal vectors. Now the next point is orthogonal subspaces. We all know what is a subspace. Subspace is the one which is just like a subset, but it obeys the rules of addition as well as the scaling. So now with respect to these orthogonality, we are learning what are subspaces. Every vector in one subspace must be orthogonal to every vector in the other subspace. Meaning is, consider the subspaces of any of the dimensional coordinate system. Let's say subspaces of R3. Subspaces of R3 can be a one-dimensional, zero-dimensional or two-dimensional, or it can be of three-dimensional in length. So subspaces of R3 can have any dimension in between 0 to 3. The subspaces are represented by, it may be a line, it may be a plane through the origin. And we can say that the subspace 0, the subspace 0 is orthogonal to all subspaces. And the line can be orthogonal to other line, or it can be orthogonal to a plane, but a plane cannot be orthogonal to a plane. The meaning of this is the subspaces can be anything. So we can consider A is a subspace and B is a subspace in any of the dimensional, let's say in three-dimensional. Then it can have some values, it can have some vectors which are there already in R3. Same with B, and these two are said to be orthogonal to each other if every element, let's say it has u, v, w and all, then it has u dash, v dash, w dash. Let's consider some other vectors. Then this u has to be orthogonal to u dash, this u has to be orthogonal to v dash and all. So every element of this A, to make this A and B as orthogonal subspaces, every element of this A or every vector of this A should be orthogonal to every vector of B and even the vice versa. And if this A can be of any dimensional, it can be a 0 dimensional, it can be with 1 dimensional, means it can have just vectors representing the lines, or it can have the vectors representing the planes. If it is representing just the lines, then it is 1 dimensional. If it is representing just planes, if it is representing the planes, then it becomes 2 dimensional. Similarly, the B. So the dimension of this A, let's say in R3, it can be anything between 0 to 3. If it is representing nothing, a null point, or if it is representing nothing, then it is a 0. Then if it is representing the lines, it is of 1 dimensional. If it is representing the planes, it is 2 dimensional. It is representing the 3-dimensional things, vectors, then it is 3-dimensional. And by default, we can say that it may be anything. We'll be having, by the property, we know that 0 vector is present in all the subspaces. And this 0 vector, if this 0 vector, we know the condition for orthogonality. If this A gets multiplied with 0, then if it is multiplied with 0, we get 0. Means 0 vector is orthogonal to all the elements. 0 is multiplied with B, or B is multiplied with 0, will get a 0. Means 0 is normal to all subspaces, is the meaning. And the next thing indicates that a line can be orthogonal to another line. So for this, we'll be seeing this example. So let's discuss that. Two subspaces V and W of the same space Rn are orthogonal if every vector V in V is orthogonal to every vector W in W, such that V transpose W is equal to 0. Means, let's say U, two subspaces V and W of the same space, means the spaces dimension is same, of the same space Rn are orthogonal. So let's take V and W. Let's V is equal to this and W is equal to W1, W2, W3 and so on. If U and V are the two subspaces of the same space, let's say Wn of n dimensional, then they are orthogonal if every vector V in V is orthogonal to every vector W in W. Means if the V1 is orthogonal to all these W1, W2, Wn, and if this V1 transpose, W is done, or it can be W transpose V1. So this is equal to 0. Similarly, V2 transpose W is equal to 0. Means every element of this V1, when it is multiplied with this W, will give 0. Will make it as 0. So V1 transpose W should be equal to 0, V2 transpose W should be equal to 0, or it can be, if this V1 is, if W1 is taken, it should be equal to 0. The meaning of that. The same here, suppose V is the plane spanned by 1, 0, 0, 0 and 1, 1, 0, 0. Then if W is the line spanned by this 0, 0, 4, 5, then when we take this 1, 0, 0 or this, when we take the transpose of this with W, will get, it's clear that V1 to V2 there is a plane and W is a line. But when these get multiplied with this, like when this row gets multiplied to this column, we know this has only the elements in the first, like non-zero elements are there only in the first two places, and here those are 0. When these two are multiplied, only these two can be non-zero, but here they are 0 and here they are non-zero, but in this plane the rest two are 0. So when these are multiplied, we are getting 0. So V and W are orthogonal to each other. So V subspace is orthogonal to W subspace.